So if you go onto Canvas, you're going to see that I'm going to give a lecture today. And when I give that lecture, I'm going to come into Module 1. Then I'm going to go under Lecture Notes 1. And what you're going to see here is that right here, there's going to be a Zoom link that will allow you to watch this video. And anything that I write down on my tablet, I'm going to attach the notes right here. So that way you'll have everything about this lecture. Then of course, on Thursday, I will repeat the same process and then throughout the semester. So one of the things that I wanted to say here is that I apologize for sending such a late message to introducing you to Physics 10. It turns out that 2 weeks from yesterday, I had just finished teaching Physics 4C in the summer. And I really had to do quite a bit to get ready for the semester. So that was the reason for the late message. Usually I like to send a message about 2 to 3 weeks before the class starts. It was impossible since I was in class. Okay, so what I'm going to do now is that I'm going to go in and I'm going to start giving you sort of like a pre-lecture before we start actually chapter 1. And I essentially want to talk about 3 things. And let me go share my screen with you now. Wow, I am not seeing the things that I'm supposed to be seeing. Okay, I believe you should be seeing my screen now. Okay, so what I'm going to do here is that I essentially want to talk about organization of my lab. And let me, again, I'm a little rusty since I haven't been teaching for just a few weeks here. So I just want to make sure that I'm organized before I get started. And then here we go. So I want to organize my lecture as follows. So how about if I start writing that? So I want to organize this lecture as follows. And this is really the pre-lecture, because I think we need to talk about 3 things before we get started, where we actually get into chapter 1. So I think the first question that we should answer is, what is physics? Because typically when I ask people, what is physics? A lot of times people say, oh, it's math. And it turns out that that's far from the truth. Okay, and then the second thing that I want to do here is I want to talk about the scientific method. So why should we talk about the scientific method? Science has a process. It doesn't matter whether you're talking about physics, chemistry, biology, geophysics, engineering. They all use the same principles of how to do things. And then the third thing that we should talk about is we should talk about the role of mathematics. This is really, really important. Okay, so what I want to do here is that I want to go in and answer each of the questions. So here we go. So here's my question. My first question that I'm going to try to answer is, what is physics? And the answer is that it is the study of all nature. What do I mean by nature? I mean the nature of light, the nature of the universe, the nature of atoms, whatever it is. That's what I mean when I say all of nature. But at its most fundamental level. And I'll try to explain this as we go along here. So I would say then, if we're talking that physics is about the study of nature at its most fundamental level, then I have to claim that the basis of all science is based in physics. And you might be saying like, wow, well, of course he's going to say that. This guy's a physicist. And I'm going to say, yep, of course I'm going to say that. So what do I mean by these statements here? So physics, one thing that I really love about physics here is that physics has very few principles. And that really suits me well. I don't have a great memory. But if I understand principles, then I don't need a good memory, because I could go back and go like, well, this is what this principle says, so that I should be able to go in and look at that thing. So if physics is the basis of this thing, maybe I should have drawn an upside down triangle. What I would say here is that then probably the next most basic science has to be chemistry. And you might say, why is physics more basic than chemistry? Well, if you look at chemistry, a large part of chemistry is how electrons interact with electrons from one atom to the other. So if you go back, chemistry doesn't really pay attention so much to what an electron is, but physics spends a lot of time on trying to understand what an electron is. We don't know what it is, we know what it behaves like. So chemistry uses that information to talk about a more complex situation where they're talking about, atoms and atoms or molecules and molecules interacting via these electrons. But at its fundamental core is the electrons. But that's exactly what chemistry does, or physics does. And one of the things that I would say here is one of the issues why I would never have gone into chemistry is that you have many things to remember. They have many principles. And like I said before, my memory's not that good. And therefore, I would never go into a field like that. Not because it's not interesting, it's just that that's not something that suits my style. And then if you go to the other basic science that people talk a lot about, you get to biology. And biology, oh, good God, that is definitely a complex science. In fact, biology is more integrated in science than chemistry or physics. What do I mean here? Well, if you want to understand biology, you need some physics principles. If you want to understand biology, you need some chemistry principles. And if you want to understand biology, you need the biology principles. And that's what I mean by biology being a very integrated science. It uses a lot of the sciences in order to explain these things. Like, let me give you an example. The heart. The heart is effectively an electric pump. So in order to understand what do I mean by an electric pump, you need to understand essentially the electricity of the heart. That's where physics comes in. And then at the same time, the heart moves, oh, good God, I forgot the name of them. They move particles across a membrane via chemical interactions. You need chemistry to do that. But then you start to look the biology of this, of how this heart, this muscle is twitching throughout this whole process and how it goes. So you need the biology of it. So as you go down this tree, you start to expand in many directions, but it always comes back down to physics being the basic stuff here. That doesn't mean that if you understand all of the physics that you automatically understand chemistry and biology. That's far from the truth, even though some people will tell you that that's the case. That's just not true. So the question is, what do I mean by physics still? I've sort of like not really giving you an answer, but maybe what I can do here is that I could ask, what are some of the questions that physics can answer? So maybe here's some of the questions that physics asks and solves are, let's say, one that's really quite interesting. Why is the sky blue? Right? That seems like such a basic question. Surprisingly, the sky is really not blue. And you're probably, listening to this instructor and going like, wow, what's this guy on here? Well, it turns out that the sky is more violet than blue. So when light comes from the sun and it interacts with the molecules, there's a light scattering process. And the light that gets scattered the most is violet. It just turns out that our eyes are designed to see blue better than violet. So therefore, we see a blue sky instead. So just by looking at the very fundamental questions of what is light, how does light interact with atoms, we could then answer some of these very fundamental questions about nature. Another one that's also really cool are rainbows. Now you could go online and you could read about rainbows, right? You can look at images and of course they're quite beautiful and you might even see 2 or 3 rainbows in the sky. I think the maximum that I've seen is 3. So 1 rainbow and then there's secondary rainbows. But what people fail to realize is that with rainbows, you may not realize that if you have a single rainbow, physics tells you that all kinds of light behave exactly the same way. I know you've heard of ultraviolet light or UV light because that's the cause of sunburns. And you probably have heard of infrared waves because those are known as heat waves. So when you look at a rainbow, to the right of the rainbow, there's an ultraviolet rainbow. And if you look to the left of the visible rainbow, there's an infrared rainbow. So by knowing a little bit of physics, you look at the world and the world is more beautiful because you know it's there. And that's really shocking. But that's, again, the very fundamental interactions of light, how light interacts with materials here. And then another one of my favorite questions of all time is, where do atoms come from? I mean, that's a really, really deep question. It's essentially, where do we come from effectively? But let's not get into a philosophical debate here. The answer goes something like this. If you look at my wedding band, for example, it's made out of gold. Gold cannot be produced here on Earth. So the question is, how did the gold get here to Earth? The Earth can't make it. It doesn't have the sufficient pressure and energy to actually do that. And to make a long story short, the gold is really stardust that effectively has settled here on the earth. Now, it's more complicated than that. And so there's a long story of how atoms are made and how they got to be here on earth. That is a deep and really, really interesting question. Another question that I think is quite fascinating is Faraday's law and power generation. And a lot of times people think about electrical power is essentially in terms of batteries. I have a battery, so therefore I could put it into my flashlight and I could produce, light, or I could recharge my battery, and that's not in my cell phone, and I could make it work. But where does most of the power come from? Well, the basic law is Faraday's law. And 93% of all electrical power in the world is generated by power plants using Faraday's law. So if you look at Moss Landing, well, Moss Landing is a Faraday's law generator. That's how it produces power. So these are some of the very basic questions that we could ask, using physics here. So let's go to the next one here. The next one that we talked about is that we talked about the scientific method. And the scientific method, I would say here, is a 4-step process. Almost everybody writes this down as a 3-step process. I'm going to write it down as a 4-step process because there is the first step that people typically ignore. So I'm going to incorporate it. So here we go. So this scientific method was really developed for the first time by Galileo, which is in the 1600s. And Galileo, by most experts would tell you this, is definitely the first modern scientist, even though at that time they weren't called scientists. At the time of Galileo, they were known as natural philosophers. It wasn't until the 18th century that people started calling natural philosophers scientists. But Galileo is really the guy that really first used the scientific method. And it goes something like this. The first thing that you got to do here is that we want to study something that really interests us, and we know very little about. So it's got to be a question that you really want to know the answer to, but you don't know very much about it. So in science, all of the most interesting questions are questions that we don't know usually almost nothing about. So the question is, what is the process that you use to do this? Okay, here we go. So then here's the first step in the scientific method. What you do here is that you make a hypothesis. And a hypothesis is always an educated guess. Now, I don't know how you operate, but I'll tell you how I operate. If I know very little about something, I'll make a guess. And then inside my head, I immediately make a consequence of the hypothesis. And that's what brings me to the second step. So then as soon as I make a guess, I says, well, if this is true, then I make a prediction. And remember, this is usually what happens inside somebody's head. And what this prediction is a consequence of the hypothesis. So what typically happens is it goes something like this. I go this way and I make a guess and I go like, well, if that's true, then this has to happen. I go like, oh, no, that's not right. So then immediately, now that I have more information in my head, I go back up and I try to make another educated guess. And now I'm a little bit brighter because I know what's going to happen here. I know that it can't be the first prediction because I knew that was wrong. So then I take my hypothesis and I make it stronger by rethinking it. So what you'll find here is that there's these series of ups and downs. You'll see online as well as, in videos, they'll say like, oh, the scientific method goes, you make a hypothesis, you make a prediction, and wow, it just doesn't happen that way in reality. And so there's a lot of back and forth, So this back and forth happens numerous times. And then once you do that and you go back and forth a whole bunch of times, then there's the ultimate test of science. And that's step 3. Step 3 is that you now perform an experiment. And this is what makes science science. Science is about evidence-based knowledge. No thinking that this is fake or whatever it is. That's just not true. Experiment is the core of the scientific method. And what it does here is it tests the prediction. So this is the key to the whole process right here. Science is not a very clean process. It's a very messy process. There's a lot of educated guesses and stuff like that. And a lot of times is that, I want to say this here is that when predictions pass the scientific method, test numerous times. And what do I mean numerous times? Well, there's a model right now that explains particle physics. That model has been tested since 1979, and it's been tested trillions and trillions of times per day. So when the predictions pass the scientific method, only then do scientists call them theories. Only then, okay? And if they're really good, really good, then they call them models. I am sick and tired of people saying they got a theory. That's a bunch of bullshit. That's a misuse of the word, especially in the media. You're hearing people say like, well, I got a theory. Well, I don't give a damn if you got a theory. The fact is, what we mean by a theory or a model is that it has to be evidence-based. You can't just come up with the theory. You can come up with the hypothesis, but a theory has a very clean definition. That word has been misused too many times. And I'm trying to take a single step here to try to correct that. So only then in science do we call them a theory. So what I want to do here is that I want to show you what I typically do to try to explain the scientific method. So what I would do here is that I would give a class demonstration. Okay, and then this class demonstration, what I would do here is that I have a, so we use a copper pipe and drop two equal mass objects. So what do I mean by that? So one of these objects is a wooden cylinder, and the other one is a magnet. Okay, you would drop it. And so here's what you would find here. So what you would find here is that I would have my copper rod or my copper pipe. And what I would do here is that I would come in and I would put my wood. Now, a piece of wood is lighter than a magnet. So what I typically do here is that I put in a piece of iron in there. Okay. And so what I do here is that if I look at this thing, this guy right here is my copper pipe. This guy right here is a weighted wooden cylinder. And the weight of that wooden cylinder is the exact same weight as the magnet. And so what I'm going to do here is that I'm going to let it fall. So it's going to drop, it's going to come all the way down, and it goes all the way through here. So what you're seeing here is that, so this dropped cylinder takes about half a second to fall through. Okay, so it takes half a second to fall through. Now, what we're going to do here is that we're going to repeat this by dropping a magnet. Remember, it has the same weight. So now the only difference here is that, again, I have my copper pipe, but now I have my magnet. And so I'm going to say that the big difference here is that now I have a magnet. And so as I drop this thing and it falls, one of the things that you find here is there a dramatic difference. And what you find here is that the dropped magnet takes 5 to 10 seconds to fall through. And most people will go like, wow, what just happened? So here I go. I go to my step one. I want to study something that I find interesting. So then I go through the scientific process here. And in the scientific process, I'm going to ask the question, why does the magnet take so long to fall through? And I know that's kind of hard to visualize. That's why I have a video here. So let me show you this video. So I'm gonna pause it here pretty quickly. So you could see here, here's a copper pipe right here. And this person is going to drop it. And then remember, I'm going to pause this thing here pretty quickly. So here we go. So here we go. Oh, man. Sorry about that. I should have downloaded it. Here we go. Oh, what's going on here? Okay, here we go. Okay, so he's going to drop the magnet. So you can see the magnet right there. Here's the copper pipe. So let's check it out. You see how long that took? Look at that. He's going to drop it right here. Look at this. Look how long it takes. So that takes a surprisingly long time for it to fall. So then we come back here. And now what we want to do here is that we want to make a hypothesis. Okay. So the hypothesis then, I'll tell you what most people think for the hypothesis is that they go, okay, so what's my hypothesis? The hypothesis is that maybe the magnet is rubbing along the sides of the cylinder. In other words, they're saying that friction is what's slowing down the magnet. And you're going like, okay, if that's the case here, what happens if I then get a smaller magnet? So then you come in here and you say, okay, I want to make a prediction. My prediction is that if we use a smaller magnet, it will fall faster. Okay. So then the scientific method then says what? Let's go do an experiment. So let's go back to the video. So if I go back to the video here, now we're going to look inside the tube as it's falling. Check it out. And you can see here that the magnet does not touch the sides of the tube. And so what happens here is that we got to come back to so what the experiment tells us here is it tells us what? The experiment then comes in and says that the magnet still takes 5 to 10 seconds to fall. So what does that do? That means that we immediately go all the way back up to the hypothesis. And then you get the back and forth between your hypothesis, and it's a very messy process where you just keep going back and forth, back and forth. That's what I mean by the scientific method. Science is evidence-based. If you have no evidence, it's not science. So it's super important that people learn that physics, science in general, is evidence-based. You can't come up with the theory because that's bullshit. You have to do better than that. And that's what scientists do all the time, whether it's physics, whether it's chemistry, whether it's biology, or whatever science it is. Okay, let's go to the last piece here. And I want to talk about mathematics. Mathematics versus physics. As we already said here, physics is the fundamental study of nature. So what this really means here is that it means this. This means we use physics concepts to describe a physical phenomena. And I got to be very specific here, because when I say describe, what we mean in physics here is that we have a physical picture in our heads. So our goal here is to have a physical picture. Everything is about the picture. So in essence, when I think about physics, there's a flow chart of physics. So physicists spend a lot of time developing the picture. So let's write this out. So I have some physical phenomena. And our whole goal in this physical phenomena here is to develop what? A picture. Using our physics concepts. Once we get that picture, we call it physics. In fact, what you'll see here is that in the language of physics, as soon as you get that picture, what they'll say here is that they'll say, physics is all done. And there's an acronym for it even. So as soon as you get that picture, we say physics is all done. So now what a physicist does is that they start to think about a crank, a flow chart. So now we go through this process of what we actually do here. So then here we go. Once you got the picture, we need to put it into a universal language. So that means my flow of process here is that now we write an equation. So that picture is translated into equation. Why do we translate it into equation? Because it's a universal language. And as soon as we get that equation, what we do here is that we then go in and we solve the equation. So then we come in and we solve this equation. And what's super important, we solve this equation to get a number. That number is extremely important. This number is extremely important. But when you put it all together, all of this here is what we call mathematics. And the whole reason of this flow chart is to show you that physics is not the same as mathematics. So the number that we calculated is connected to the equation that we wrote. The equation that we wrote is connected to the picture that we visualized in our process here. So let's look at this thing. So what I would do here is that, why is that number so important? And the answer is language, everyday language is ambiguous. And what I'm saying here is that everyday language has words that have double meanings. Right? They have double meanings. And so what's important about this whole process here is that you get something like this here. What you find here is that, let me give you a silly example. Maybe that's the best way to do this. And this is definitely a silly example. Somebody may say, hey, Carlos, you're a fat dude, right? You're a fat dude. Well, I know what I'm thinking. They probably mean PH-A-T, fat, meaning that I'm a rad guy, I guess. Or they probably mean that, hey, you're a little thick on the waist here. But that makes that phrase right there, makes it ambiguous as to what the real meaning is. So why do scientists use the number? And the answer is that numbers never have double or obscure meanings. And a very clear example would be a pencil. So, for example, okay, measure a pencil. So let's say that we have a pencil. Okay, so I have a pencil, it has this eraser, then it has its body, then it has a lead here, and let's say that we have a yellow pencil. Then you come out with your ruler. Then you come in here with your ruler, And when you measure this ruler, you use this ruler, you find out that the length of this thing is 6 inches. Once you measure that pencil and it's 6 inches, what's there to debate? You can measure it, she can measure it, he can measure it. And that ruler always claims that that pencil is 6 inches long. So that's why numbers are so important in science right there. So to summarize this, in this course, we are not interested in solving mathematical equations. I'll leave other physics classes to do this. This is a course in conceptual science. So we're mostly interested in the concepts. We will use equations as pictures that guide or that help to guide to thinking physics. All of the equations that we will write are just pictures that we're going to use. So when I say I'm going to use an equation, that means this equation right here is really a picture. I see the equation as a picture, not a mathematical process. By the way, we are going to use mathematical operations. And what I mean by that, I'm expecting you to be able to add and subtract certain numbers, multiply, and do some division, but they will all be relatively easy, mathematical operations.